In this video, this tutorial, we're going to look at Poisson distribution, level 3 statistics. I'm working from examples from the ESA learning workbook. I'm using the booklet, so I'm looking at page 18. If you've got the ESA workbook with lots of standards in it, it'll just be exercise F under the probability distributions. Okay, so there are 4 characteristics with Poisson. So here they are listed. Events occur at random and they're unpredictable. Each occurrence is independent of others and they cannot happen simultaneously, cannot happen at the same time. The rate is constant. For a small interval, the probability is smaller, proportionally. Okay, the rate is less. So what this means is, if we expect there to be 6 earthquakes in a 2-year period in a particular country, then in a 1-year period, we're going to expect there to be 3, proportionally. Half as long an interval, half as many for the average. Same as if we went, well, a 4-year period, it's going to be twice as many. So we're going to expect to have 12 earthquakes. Okay, that's on average. We're given this formula on our formula sheet, and we can see here that x is discrete. It means we can only have whole numbers. And there's only one parameter in Poisson distribution, and we call this symbol here lambda. Now, lambda is the mean, the average number of occurrences of something. It's also the variance. Okay, so if we remember some things about variance and standard deviation, our formula sheet doesn't tell us straight off that the variance is lambda. But if we think back, how do we get standard deviation from variance? Well, we square root it, and there we have square rooted the lambda to get the standard deviation. Okay, the main thing is that lambda is our average, our mean. The mean times, or the rate at which an event occurs. And the rate's over a given time period, or length, or an area, which is a continuous measure. It's a measured interval. Discrete data over a measured interval. So, number of earthquakes, we count them up, it's discrete, over a year. Number of defects in a 20-meter roll of fabric, etc. Okay, if we think back to characteristic 4, and we know the rate of cracked eggs that arrive at the supermarket in a week is 70. 70 in a week. Then the rate of cracked eggs that arrive in the supermarket in a single day is 1/7 of that. We expect to get 10 cracked eggs arrive at the supermarket in a day. Okay, so here's the formula that we're looking at. Lambda, that's our average, to the power of x. X is our number of interest, exactly 6, exactly 9. E to the power of negative lambda, all divided by x factorial. Okay, so let's have a look at the example from the ESA learning workbook. It says there's an average of 6 shark attacks per year in Australia. Okay, so our lambda is 6. Now it's saying, what's the probability there are 9 in 1 year? So if we go to our little bar graph that we're so good at drawing, 9, there could be perhaps 8, 10, everything in between. And with Poisson distribution, in theory, we could go to infinity. We do not have a fixed number of trials or a fixed answer at the end. So we want, probably there are 9. We want exactly 9. So for this example, x is equal to 9. Okay, so back to the formula. E was 6 to the power of 9. Sorry, lambda is 6. 6 to the power of 9 multiplied by e to the negative 6 all over x factorial. Okay, so pushing all that into our calculator. If we look at this calculator here, so we are going to, let's bring the formula back where we can see it. Lambda was 6. 6 to the power of x to the power of 9. Make sure you come down off the power. We want to multiply this by E, and E is right, a bit hard to see on the screen there, but it's behind the natural log there, so I'm going to have to use the shift button. E to the power of negative lambda. Negative lambda was 6. And we're going to divide all of that when we come off the power. Divide all of that by x factorial. Now that was 9 factorial. So our factorial button is right there on this type of calculator. So there we have a probability of there being exactly 9. So exactly 9, what are we looking at? Shark attacks. So there's our formula. It's equal to 0.0688. 4 decimal places would be great. Okay, so the second one is slightly more complicated. More than 2 in a year. So if I change colours and we draw what that might look like. More than 2. We could have 0, 1, 2, 3, all the way up to infinity. More than 2. 2 is not more than 2. 3 is, 4 is, 5 is, all the way up to infinity. Now, because it goes up to infinity, we can't work out all of those values individually because it goes on forever. But what we have to do now is remember, all probabilities add to 1. So if we go 1 minus this, this, and this, we will get what we want. 1 minus the probability that x is 0, x is 1, and x is 2, and we have the answer. So we're going to go through a series of problems, and we're still going to have lambda equal to 6, and x is going to be equal to 0. Then x is equal to 1, and then x is equal to 2. So if you look at your workbook, for example, there, number 2, we get the probability using the calculator method that we've got an answer of 0, the probabilities here, 0.0025, 0.0149, and 0.0446. We add all of those together, we come up with 0.062. Now remember, that's just for those 3 green ones, and we want all the black ones. So we want to now subtract away. So we want to go 1 minus 0.062, giving us a final answer of probability of 0.938. Okay, so when we're using the calculator here, try and work out how you can go back, and we can't really go back. Work out so that you can go backwards through your equation to keep changing your numbers. So I can change this to 0 for x equals 0, and if I keep going back through it, lambda stays the same. Here, change this to 0. So just take shortcuts trying to manipulate your calculator as well. Okay, so there's the first one that we wrote down there. Was there 1, 2, 3, the negative 3. So there's the 2, 5 being rounded off. Okay, so that's Poisson distribution. The next topic we're going to look at is the inverse of Poisson. So have a look at that video when you've completed this chapter, but you'll need to have lots of practice in this chapter first.